problems with standard model. So today we'll talk about matter-antimatter symmetry. So what is this problem? Why is this a huge problem in the standard model? Why do you want to call it as a problem in standard model? Sorry. Hello? Yeah, tell me. Sorry. Some guy just came landed up here. Okay. So, is this a problem? First, to begin with, in the standard model, there is nothing which really distinguishes particles and atoms. So the moment you put in quantum mechanics plus SPR, this predicts antimatter. Now, matter and antimatter are symmetric for all practical purposes. In QFT, they are completely symmetric. You cannot distinguish between matter and antimatter. Okay? You cannot distinguish them. So under all symmetries, when I say symmetry, they are unsymmetric. So the only thing which distinguishes them is essentially the two symmetries, which are charge conjugate symmetries and CP. If there is any violation of these symmetries, okay, most theories, vectorial theories like QCD, QED, conserve these theories, but there is only one theory which violates this one, which is the weak interactions. If there is any violation of these theories, otherwise we know that in quantum field theories, CPT is always conserved. So matter and antimatter should be always be equal. They are always symmetric in nature. If, unless, so C and CP are violated, there is a problem. There could be asymmetry. But that's also mine. We know that it's only violated by weak interactions. Only weak interactions violate. Now the point was that initially, so to begin with, you would assume that somehow this so as far as P3 is concerned, like as far as if you neglect weak interactions which are small, you should expect equal amount of matter and antimatter. So why is that? That is also based on Big Bang cosmology. So Big Bang cosmology plus observations. Observations here are expanding universe. Let's forget about acceleration, but we know it's expansion. Okay. Big Bang cosmology plus observations, which is essentially observations of expansion of the universe, tell you that universe started with a symmetric phase. When I say symmetry, matter, antimatter symmetric phase, essentially it's a gas of photons. So, which can annihilate into matter plus antimatter in thermal equilibrium in an expanding universe. So there is, so if you believe in Big Bang cosmology, which essentially starts with, so there is enough evidence actually for Big Bang cosmology. We observed CMB, okay? So CMB is a very big evidence for Big Bang cosmology. So we know that we started with a gas of photons in an expanding universe. So if there is a gas of photons, always matter and antimatter are not very far because they always annihilate into photons. So there should be equal number of matters and they will always be in thermal equilibrium, okay, within the universe as far as they are within the rate of expansion. Okay. In an expansion, so this is how is Big Bang cosmology. So based on this, what you would expect is that you should expect Big Bang cosmology expects that we should be able to produce equal amount of matter and antimatter. Should be able to produce equal amount of matter and antimatter in the universe. Now, observationally, this is in very significant contrast. Observations wise, so people started looking for the amount of antimatter content in the universe. So the antimatter content in the universe has been looked at by balloon experiments, cosmic ray experiments, and so on and so. But the most important experiments come from satellites. So one of these satellites is stationed on the International Space Station, which is called AMS, sometimes also called the collider in the sky. Okay, which is a particle detector in the sky actually. So it is so precise. So you know who runs AMS? He's the same guy who discovered champ quark. It's called Sam Ting. You've heard of Sam Ting? Sam Ting, anybody? It's a very famous personality. He is also in charge of AMS. So if you remember your particle physics course, you hear his name associated with deep side. He's the same guy as running AMS. So AMS looks for antibarium, antiproton. This I am loosely calling as antibarium content, or also and anti-electron content around us based on satellite. It's a satellite detector actually. It's a fantastic equipment. So there is an observer completed version. It's called AMS02. Now, if you look at their graphs, actually, I don't have them unfortunately. If you look at their graph, they have a positron fraction. Or positron fraction, I think we talked about it the other day when we were talking about dark matter. So, antiproton fraction also. By the way, antiproton also was measured by Pamela, an Italian experiment, which was before AMS. AMS done it much faster, much better, much precise. So, look at the antiproton fraction. The antiproton fraction comes out around 10.6. I don't have the plot or something, but you can look at it. X-axis is the energy. This is the fraction. So at different energies, this fraction changes, but roughly of the order of 10 power minus 6. So it's an energy spectrum, okay, which gives out, this gives out an energy spectrum. Unfortunately, I don't have, if I have a projector, I can show this plot. So these experiments tell you that the amount of antimatter around us is of the order of 1 in 1 million. At least in the anti-baryon content, it's around 1 million. It's a little bit small. Okay. So if the Big Bang started with equal amounts of antimatter and matter, somehow the antimatter has dissipated, it's gone away. Or it could be that, so some people propose the idea that there are domains, very large domains of antimatter. So just there is a domain of matter. So there will be a nearby domain, but dominantly of antimatter. You will have anti-hydrogen, you will have anti-helium, anti-galaxies, so on and so on. Galaxies made up of antimatter because they are very much symmetric. Because as far as dynamics is concerned, you don't have to worry about it. And you can go through everything. Big Bang represents galactic represents everything you can go with antimatter. Okay? So these ideas were also proposed, but typically these domains, turns out that these domains, sometimes I think it's called patchwork. Patchwork universes. So these are patches of universes which are made up of matter, only dominantly matter, okay? And then there is a nearby universe which is made up of antimatter. But then somehow there is some interstellar medium between these two, essentially. So there should be some rate of annihilation. So some annihilation should happen. So you can estimate what is the size of this force from the diffuse gamma ray flux. What is the typical size of this universe or this patch? It turns out these patches themselves, say for matter, they should be of the order of the size of the universe. So you cannot really have, unless you have a separate universe of antimatter universe. Okay, these patches themselves should be of the size of the universe. Patch size. These are the order of the universe. So this is from, say, diffuse gamma ray spectrum. So this is from the annihilation of the interstellar medium. Okay, so let's assume that there is some asymmetry. Yeah.
Universe size, observable universe?
Observable universe size. Observable universe size. These observations. Let me make it clear. Of course, one can still play a role. Meaning, there could be there could be more complicated scenarios in the probability creation and so on. So we have matter and antimatter models, and so. But let's not worry about it. So let's just these are based on estimates of observations. So if there is an asymmetry. If there is an asymmetry, what is asymmetry? So this asymmetry, if it started at Big Bang, okay, asymmetry started at Big Bang. Big Bang, and now has led to the observable universe, because the entire observable universe is essentially made up of baryons. Okay, so this asymmetry NB minus NB bar NB plus NB bar. So at the round of say around T1 G or something. Should be equivalent to. So I define an asymmetric quantity, which is the difference between baryons and antibaryons, the sum of it, should be equivalent to the present day NB by N bar. This is essentially your critical density. What is it? Okay, number of photons, total number of photons. NB plus NB bar should be equivalent to your photons, number of photons. Okay, this is around CMB temperature. The present CMB temperature. So this quantity is called eta. So the most important quantity. Every time, in every theory, we will calculate this eta. Okay, if you want to explain variances. So this is what we calculate. And this quantity turns out to be extremely tiny, both from CMB as well as from primordial nucleus. Okay, both these measurements give you this number of the order of 10 power. So there is a baryon asymmetry, which is sort of coming from two observations, coming from CMB, nucleus essentially. So this is coming from say light elements. So this is essentially helium, lithium, barium, deuterium, so on.
Ideally, it should have been zero.
Ideally, it should have been zero. But if it is zero, we won't exist actually. So, yeah. So sometimes you keep hearing in popular lectures, you say that this number is the reason why we are existing, and so on. So, okay. So physicists discuss the origin of life and all this. Okay. Weak interactions are equivalent to life and so on. So all these statements you keep hearing, so all these correspond to this number. So it's a very, very tiny number at the beginning of Big Bang. Okay. And then one has to, in a theory, say for example, if you want to calculate this one, you generate this number at the Big Bang, then use Boltzmann equations, solve it, and get what exactly.
10 to the power minus 10 is at the time of Big Bang.
Even right now, it's only That's the original at the time of Big Bang, when the light elements were formed or when the Big Bang represence is happening. Right now there is no antimatter, so the antimatter is suppressed by 1 in 10, 1 million, like I said. So these are the time of Big Bang. So it is very, very small at the time of Big Bang. Okay. It is large now. It's yeah, it's a large now of the order of yeah, roughly if you want this fraction, antimatter by matter fraction is roughly of 10 power minus 6. So 10,000 times smaller. Around that. Okay. So how do you generate this asymmetry? So there are these famous Sakharov conditions. In BBN, in Big Bang, essentially, at the Big Bang cosmos, how do you generate this? So you can prove these three conditions. These are called Sakharov conditions. You can actually prove them by writing a density matrix and so on. So, okay. First condition is called baryon number should be violated. Two, CP should be violated. Out of UV. So as long as the process is in equilibrium, it won't. It will be generating equal number of forward rate and backward rate. So any annihilations or any decay or something, the forward and backward reaction would be the same. So this is obvious that it should be out of equilibrium. So that it should follow its decay rate should be smaller, greater than the expansion rate. C and Cp should be violated because we saw that if C and Cp are conserved, a matter and antimatter, there is nothing to distinguish them. But the third most important condition is that baryon number should be violated. Okay, if baryon number is not violated, you cannot distinguish baryons and antibaryons. So somehow you have to generate larger number of baryons compared to antibaryons. So these three conditions should be considered. This is it. Generally you can prove it. These are written in 1960s, 1967 or something. I don't remember the Sarko's conditions. And okay, this reference which I am following at home is nice. There are several references on retrieving variances, but I can show. But I like can it be? I'll put it in the. This is a nice report. This is a very nice review. Of course, there are many other ones. More popular ones are Pasquale-Di, okay, and then there is also one by Buchmuller and Blumacher. Very famous physics reports, Blumacher. And then in Pasquale-Di and Buchmuller. So there are several differences. Okay, each of them has some interesting things. So, but this one is the most concise and very nice. Actually. Okay. I'll I'll try to put other ones also. Um, this is a bit old. Focuses on these things. Focus on something called lipogenesis. Okay. I'll just stop it. Then there is who is the other one? Pascal Debari, Buchmuller, and Buchmuller. It's a bit old. Buchmuller, Debari. They are all wonderful literature. So most of them start with variances. Okay. And of course, if you want to look at variances, also you can look at the textbook by Prof. So the process of generating this small asymmetry is called variances. Genesis, you know what it means. Varium means baryons. So baryons are being created. So that's the reason why we call it as life or all kinds of things. So we become biologists for a second. Okay. So these three processes, of course, within the standard model, initially people thought that the first condition itself is not satisfied by standard model. Okay, the first condition itself is not satisfied because standard model has baryon conservation. So this is not possible within the standard. So you cannot explain this phenomenon in standard. I'll come to that why. Okay. So there are three famous models of baryogenesis. Okay. They are independent of any physics beyond standard model. Okay, these methodologies, three. Okay, in a way. Okay, in a way. So these three models I mentioned, they are slightly model independent. So then we will see why each one will fit or fit off. So you take any nice model you want, try to get this kind of phenomena working. So the three main mechanisms of baryogenesis are called gut baryogenesis. So in all these models, what you want to explain is this small parameter. You check in these models whether you violate these three conditions, okay, and then whether you can generate the correct epsilon eta value. So that's the basic idea. So the first one, let's look at the first one. This I don't think you'll find any reference now. Actually, gut variances. It's a very old topic. You will find it in some Raymond's or Graham Ross academic materials. Then also there is this paper, the book of Palash Paul and Mohapatra. Okay, and also this one. This one also has it. Coven tunnel has it. So what is the idea here? So let's consider all guts Y B and most of the guts, violet, B1 and B1. Okay. So how does it happen? So let's take an example of an SU5. Okay. Example. In this model, the matter sits in the representation. Matter sits by bar of SU5 and 10 representation of SU5. Okay, and the adjoint of the theory is what of SU5? 24. So the gauge is sitting here. Okay. So under 10, what are the particles which sit here? Q, UC, EC. Okay, I'll tell you what these are. I'm just using some notation, but don't worry. BC, L. I'll elaborate it in a second. Under 5 bar, you have right-handed down-type quarters. So all the three colors, be right-handed. Okay. Star C means charge conjugation. Okay? So for some reason we write it in this particular notation. So this is from red color, right-handed also, and also some one color. So let's one color, DR2, third color, and the electron left-handed, neutral. 10, you can represent it in terms of some anti-Semitic representation. Has again Q. So you are 1, you are 2, you are 3, and then you have Q1, Q2, Q2. I don't know how many I'm putting. 1, 2, 3, 4, 5, 6. Did I get all the 15 right? Sorry, left-handed. So this is UL, DL, DL. Okay, this is 6 particles. This is 3, this is 1. I am not sure whether I put it correctly, but you have to organize it in nice manner so that you get the fact back here. So the basic point here is that you have all the colored particles sitting here and leptons sitting here, colored particles sitting here and leptons sitting here. Now if you look at the gauge bosons sit in a 25-dimensional matrix. Okay, 24-dimensional matrix. So which I write it in terms of 5 by 5 matrix. I write it in terms of 5 by 5 matrix. But what I want is one gauge group to be conserved. What is the gauge group to be conserved? I want my SU2 cross SU3 cross U1 cross conserved. So that takes away 8 plus 3 plus 1. That many gauge bosons it takes. So 12 gauge bosons are gone. What happens to the remaining gauge bosons? So I want to conserve G mu, W mu, A mu. I put them in the diagonal because I want to conserve the diagonal. I can choose such a way that I conserve the diagonal. And the remaining gauge bosons are called X and Y gauge bosons. Now, what are the properties of these things? These gauge bosons conserve color. These ones conserve electroweak charge. These conserve electric charge. But X and Y connect colored particles with leptons. So they take colored particles with leptons. They clearly violate Varian number. Okay, X and Y bosons. So the first idea was that if you somehow make these X and Y bosons, you generate variance asymmetry. So this is called gut variance. So what you do is you introduce some CP violation in the gut in the Cobb potential. Okay, so that when X and Y bosons decay, the decay of X boson and there is an asymmetry between the decay rings of so the asymmetry you want to relate it to the asymmetry in the decays of this X and Y bosons. The eta would be related. So this happens at a scale of the X and Y gauge bosons have masses around 10^15 GeV. Okay, so they are there, they're heavy. So they decay to standard amount of particles. But the decay of the X boson and the Y boson would be different compared to the anti-X and anti-Y. So this will generate an asymmetry. You're happy, so you know what is it. It's all fixed. So you solve the Variances problem. But this was the solution. So the first solution came on gut variances. That instead of SU5, you take something. Okay, somewhere. So these are only one condition is there that you should not introduce any more Varian number violation or lepton number violation below the gut scale. The only Varian number and lepton number violation should come from the gauge bosons. If that is satisfied, you can get no additional Varian number and no additional B violation and L violation. This is the only condition. As long as this is true, you solve the problem of variances. So there you imagine that there is a granite field theory, it could be supersymmetric, non-supersymmetric. You generate enough symmetry. So. But then people threw a spanner into it actually. Okay, so people threw a spanner into it, started with the dot. Here I should mention the signs of Varian number violation. So what matters is that in this case the signs matter. So so these conserve B minus L. is always confusing even to me. Okay. They conserve B minus L. Okay. We talked about B minus L sometime, right? Around in one of these lectures. So there is no additional B variation and left on. But then, what Taft found was that yesterday we discussed about QCD vacuum. Similar to the QCD vacuum, electroweak vacuum is also quite complicated essentially. Okay, quite complicated because any SUN theory we said like we have multiple vacuums. So the vacuum structure is complicated. So Taft found that non-perturbative transitions vacuum to vacuum transitions violate B plus L, and this violation came out to be of the order of B plus L violation was around 10 power minus 40. I think this number is around 10 power 4 minus 40. So this won't clearly affect any B plus L violation or generated at cut scale because it is multiple orders of small compared to what is expected. What is expected by we want 10 power minus 10, but this 10 power minus 40. So it's millions of several orders of magnitude smaller than what is expected. And so if you manage to generate 10 power minus 10, this won't spoil any cut variances. Okay, it won't spoil this. That is the idea. Okay, that's the idea. But then this reasoning turned out to be wrong. This turned out to be wrong. Why? Because these transitions rapidly increase at finite temperature. Okay? These transitions rapidly increase at finite temperature. So we'll come to this idea of electroweak variances. Okay? So keep the but variances at a while. So you generated of the order of 10 power minus 10 and you're safe. Okay? So at zero temperature, you're fine. In the early 90s, after the after the Black results, essentially, so people started questioning whether one can have variances at the electroweak level itself. Because people found that, like I said, mentioned that you measured the gauge couplings very precisely, the left measured. Okay, so gauge couplings don't unify in standard model. So maybe we should look at alternatives. So Shaposhnikov and not Kuzmin, who is the other guy? Roboko. Looked at the idea of electroweak variances. What is their idea? They said, okay, there is this B plus L violation in the standard model already from non-perturbative. So let's see what happens at finite temperature, whether these barriers get modified essentially or not. So basically, we have B plus 1 transitions already. So if you can somehow enhance it and bring it to the level of conformance. So what are these transitions between vacuum to vacuum? So these vacuums, vacuum to vacuum transitions, are essentially non-linear, again, topological solutions of the retroweak vacuum. These are called spiralons. So spiralons are, so earlier we looked at solutions which are instantons, right? Essentially in the QCD vacuum case. So spiralons are nothing but soliton solutions. All the standard model things to gauge that you are, okay, which are unstable. Stable ones, because they are protected by some symmetry and winding number and so on, so they are called solitons. But these are not protected by any number, winding number or something, so these are called solid spiralons. So they are unstable essentially. They cannot be stable in any field theory. So if you want, they are solutions of the coupled equations again for the non-abelian gauge field theory. So the field equations you can write, okay, this is the dj, mu, okay, ij. So these are spatial solutions. So you set all the temporal components to 0, set all the temporal components to 0. These are spatially localized, okay, like solitons, okay, but they are unstable, okay, they are not protected by instrument. Okay. This is the source term from the fixed field. These are Fourier matrices. So I'm just writing it for completeness, but you don't have to worry about it essentially. Okay. Let me write small f ij. Small f ij. These are also for the gauge field of the UED U1. And so on. So, okay. This is the Higgs field web. So typically you also not only set the temporal component to 0, you also solve it in the limit G prime goes to 0. So U1 also is set to 0. Okay, you can then become simplified, and you have these solutions given in terms of some matrix equations. Okay, and then you can compute what is the energy of these equations, substituting solutions, what is the typical energy, and so on and so on. So what people have looked at, meaning these people have shown, is that these spiraron solutions which move from one vacuum to another, this transition rate increases drastically at final temperature. Increases drastically at final temperature. So at temperatures beyond the atomic scales, temperatures of the order of 10 power 2 GeV to 10 power 12 GeV, these transitions become so dominant, okay, that if you somehow have enough CP violation in your theory, it can generate enough asymmetry. The barrier number violation is sufficient. Barrier number violation is sufficient, become very large, so that you can get an eta of current and components. Okay. This is the idea of electroweak. The moment electroweak bariogenesis becomes important, what it does is it also kills because it goes in the opposite direction. Like I said, the gut bariogenesis will only work if there is no additional new baryon number or lepton number violation. So since there is an external baryon number and lepton number violation, whatever initial baryon number or lepton number is generated, it is washed out by this at the weak scale, because that set scales around 10 power 15 GeV. As the universe cools to 10 power 12 or something, so you'll start having the Spelleron effects essentially, which play the important role. So the initial conditions will get completely washed out, and you generate essentially what is left of. So electroweak bariogenesis, or this effect which happens in electroweak physics, washes out all the gut bariogenesis. So this kills the gut bariogenesis idea. The entire idea of gut bariogenesis is killed. Okay. And the clue here, the difference here is that it violates B plus L. Okay. We'll see another idea where they use this. They use the gut electroweak bariogenesis to convert it to something else. So it washes out any initial asymmetry generated by or any other process. If you have an initial condition, so you can ask the question that why can't bariogenesis be an initial condition? God gave this bariogenesis, okay, and eta is equal to 10 power minus 10 as an initial condition in the universe, and you don't have to worry about a dynamical explanation. Why do you want this? If it came out as an initial explanation, it's fine. Then you don't have to worry about why you are generating, how you are generating this asymmetry. The problem is our theories are so symmetric in C, CP, and so on. So you can actually calculate this asymmetry dynamically.
But in Big Bang cosmology,
Yeah. We have to put an initial condition. You say universe is asymmetric. Initially, it's symmetric, no? A gas of photons. But you say a gas of photons with a small asymmetry. Okay. But that doesn't, our theories will not allow it, because our theories are so nice, calculable, computable, and you can show all this. Most of the time, these Spelleron transitions are essentially calculated numerically. They just decide them.
so even if there is some small asymmetry in the equation,
It gets washed out by this, by the electroweak bariogenesis. But there is an important condition for electroweak bariogenesis. When you compute the, if it has to work out, there is an important condition. So it's not just enhancing the baryon number and lepton number violation, you also have to generate enough CP violation and asymmetry. So this requires something called a first order phase transition to happen in electroweak bariogenesis. Okay. So first order phase transition.
Something I just didn't understand, like if you have an initial asymmetry in Variances, and because of the high transition rate, you're going to be washed out into different vacuum, so you don't have enough.
No, it's just that you don't have to worry about different vacuum. So these vacuum to vacuum transitions will anyway generate baryon asymmetry. So the resultant baryon asymmetry would be so large, okay, that it would, it would wipe out whatever asymmetry was initially present.
Okay.
Whatever asymmetry was a small asymmetry, if it was initially present beyond that, it will just wipe it out. It won't keep it. It won't keep it. Essentially. It's not going to preserve this asymmetry. What I meant to say is, it's a small perturbation to this one. Now this is important that it should undergo a first order phase transition. So the first order phase transition means that electroweak symmetry breaking itself, when the Higgs gets aware and everything, it should pass, the electroweak transition should be a first order phase transition. So what does it mean? So what does it mean? That when you compute your one loop effective, what is the condition? It means one loop effective, finite temperature, effective potential. Okay, so you compute the one loop effective potential by some summation. Okay, so you actually do a summation. So where it's a function of something called V of a temperature. You know, there's a formula. It's very much similar to the Coleman-Weinberg formula. So you have some m square by t square log m square t square m square t square or 4. I am not doing correctly. 1 by 64 pi square. What is it? I forgot this one actually. It will be of this type, where this is the mass matrix. Okay. So you will have some form. Okay, in the field space. I can write it down once again. Let me just check. I hope these people have drawn it. Strange. Okay, I don't remember this formula right now. I used to remember it very well. Okay, earlier times, but now I don't remember. So 1 by 64 pi square something, which is a very standard. So you can compute this potential. And now when you compute this potential, you have to derive something called the new vacuum expectation value with this temperature dependent potential. So the new vacuum expectation value, which is again on the fields dependent vacuum expectation value, you will generate something called VC. Okay, the vacuum expectation value at finite temperature. So the condition for a first order phase transition is that Vc by T should be greater than 1. Vc by Tc should be greater than 1. I am removing this. I am removing the supersymmetric version of it. It's super m square. Yeah. Okay. I'll just check it. Okay. I'll send it to you by I'll let you not write it down. Okay, anyway. It's It's in Covenant. Okay, fine. No, I used to remember these things, but okay. Yeah. So this is the main condition. The main condition is that when you derive this, write down your 1 loop effective potential, finite temperature 1 loop effective potential, and then you derive the actual vacuum expectation value at finite temperature, which is called the critical vacuum expectation value. So the value, the critical vacuum expectation value, or TC, should be greater than 1 at some temperature. Critical temperature, T equals to. Now this condition gives a limit on the zero temperature parameters. Okay, zero temperature parameters like Higgs mass essentially. The Higgs mass mh should be less than or equal to 7 kg. So clearly, if you want electrowave variances to work, there are two main problems. One actually is that for the first order phase transition, because electrowave variances only happen through a first order phase transition, it requires, okay, and this could happen if the first order phase transition happens, then the spin round rate will become very high, and so you'll have a large enough Varian number variation. But for that to happen, the first order phase transition to happen, you need a Higgs mass lower than 72 GeV. Okay, you need a Higgs mass lower than 7. This is clearly ruled out. Second problem is that you won't generate the. You also keep hearing this thing. The delta CKM does not produce enough CP. So you need to produce large amount of CP violation, okay, to generate this system. Now, if your source of CP violation is the only delta CKM, okay, which is the standard model source, that's not sufficient because delta CKM is constrained. So delta CKM is constrained by the CP violation B physics sector and K physics sector by epsilon K and C. So these two together make electronic variances, which if it had worked had been wonderful because it has a dynamical explanation within the standard model itself. Okay, tell you that the standard model version of electronic variances will not work. Okay, so these are two main conditions that which tells you that. Okay, so we have seen out of the three mechanisms, two mechanisms are gone. Okay, two mechanisms are gone. So the third mechanism, which is the most popular mechanism nowadays, called retrogrades, which became popular after the discovery of neutrino masses. It can still work. I like it very much. It can still work in BSM models, some BSM models. In MSSM, it barely works. It doesn't really work. So, but in NMSSM it works. But it's a lot of work to show that it works actually. It's a lot of work. It's tremendous amount. What it says.
Essentially, you need to change the finite temperature potential in order to achieve the first order transition, which you can obtain by adding degrees of freedom. Adding higher order
Corrections also. So you need to add t squared, t power 4, all these corrections. In the recent times, there are simpler extensions which, by focusing on, meaning in dark matter, there are these models which are called Higgs-mediated dark matter, or Higgs portal dark matter. So you just add a singlet, and the singlet has H diagonals and mass square electrons. So there is Perlstein and company have looked at standard model and a singlet, just a scalar singlet, and try to look at electroweak variances in this matrix. So this is, I think, if you want the minimal extension where it can work. So it looks like even in MSSM you need to add a singlet to make it work for an electroweak variance. Something which has not been done in great detail, but yeah.
So this can change this, I mean, give a first order phase transition.
It claims that it can work as well.
But what about this extra? So
CP violation, I don't know. I don't know whether they have checked it or not.
I think the singlet is Lagrangian is CP even. The minimal extension is CP even.
With the singlet, yes.
Unless you put it by hand.
Yeah. So what you can do, I think there are dynamical mechanisms of generating CP violation. So you have, so if you have a singlet or something, you can have a Z2 symmetric potential, and you can have different domains. So you can generate when you break this Z2 symmetry, you can generate again CP violation by W nucleation. So each one would have a different CP, and there is some mechanism which can look into generate additional CP symmetry. But I don't know if it actually works finally when you do all that bubble nucleation and everything, whether you get the correct eta or not. Because these are again numerical simulations.
The 2x double model has CP on there.
Right. So the final thing is supposed to write the late 90s. Proposed by Fukukita and 90s. Late 90s, 95, 97, I don't know. It only became popular after the discovery of the neutrino masses. Okay, so this is called leptogenesis. This actually works. Okay, this is the first model which I think it works. So it has two main steps. So initially you violate B minus L. By generating lepton asymmetry. Generate lepton asymmetry. This lepton asymmetry gets converted into baryon asymmetry when the spellerons happens. Here you don't need first order phase transition, just ordinary electroweak spelleron processing, okay, is sufficient. You don't really need a first order phase transition, but whereas with a single Higgs you need a first order phase transition. So this delta L gets converted because this violates B plus L, gets converted into delta V. So you initially generate lepton asymmetry. Lepton asymmetry gets converted into delta V through this spelleron.
A couple of questions. Now, V minus L will introduce anomalies.
We know the V minus L violation.
The standard model V minus L is
Okay.
preserves anomalies or introduce anomalies, right?
V minus L breaking is explicit breaking.
By hardware.
Hard breaking. By vast terms of Marano.
Okay. Also, you said that you phase transition, first order phase transition.
You don't need first order process.
Shouldn't you get that or have that in order to obtain departure from thermal equilibrium?
Out of equilibrium condition?
Yeah.
Yeah, the out of equilibrium condition is anyway satisfied here to generate the initial asymmetry.
Initial asymmetry. Okay, because it will not be washed out.
Or it will not be washed out. So you are generating the out of equilibrium condition for the first case essentially. As long as okay. So the basic idea here is the Lagrangian of the standard mode is extended with right hand seesaw mechanism. You again have the seesaw mechanism. Okay, thanks for the clarification. So let's write down the seesaw Lagrangian. So we'll consider a type 1 seesaw. This I am writing as newer because I am writing in terms of Marana master. This is just a Marana master. Or let me write explicitly. So Marana master. So imagine that you are sitting at a scale around 10 power 10 or something. Okay, intermediate mass scale for this heavy right hand. So some mass scale, some. This may not be strict actually. I'll come. There's something called degenerate electrogenesis where you can push down all the way to TeV scale. Okay, but let's just start with this. So you start that there is some CP violation theory, and so what happens is it can have a CP violation by having decoupled. So you have right-handed neutrinos decaying into the Higgs and the lepton. And then, because you want to generate CP symmetry, plus you'll have loop corrections to this. So these are self-energy corrections essentially. So this will generate an epsilon, a CP symmetry in the decays of right-hand neutrinos. you generate this asymmetry, cracking first order phase transitions essentially. So this asymmetry will be proportional to y will be proportional to some imaginary value, imaginary component. You can write some indices essentially, some, okay. So you can write something like a jar slope invariant also here, okay, which will give you some, and then the mass of the right hand, latest right hand. See, whatever the heavier right-handed neutrinos decay into, whatever asymmetry they get generated, it gets washed away again. What remains is the last right-handed neutron. Okay, what is the least heaviest? When I say last means lightest. So the lightest right-handed neutrino, it should decay, and its asymmetry is preserved. What is the asymmetry? So what you are worried about is the lightest asymmetry. If you have flavor effects, the other two also will play a role. But let's just do simplest analysis. Okay, for as far as we are concerned, so you can generate a asymmetry proportional to the mass of the lightest right-handed neutrino. This gets converted into the asymmetry of the baryon asymmetry, and this actually works. One can actually solve the Boltzmann equations. Everything is available now. Okay, if you want, you can just plug it in and show that it works for any number of cases essentially, for any values of R's and everything. There are bounds derived. It works fantastically essentially. Okay, so what I showed you is that if you want to generate baryon asymmetry, matter-antimatter asymmetry within the standard model, it's not possible. It's not possible from ectopic variances. It's not possible through gut variances, but through leptogenesis is the best known mechanism as of now. Okay, unless we find some other new mechanisms which can give you the baryon asymmetry. So this also requires to extend the standard model Lagrangian by. There are now. What is that? It looks like naively that it can be put it in various theories naturally. Okay, you can put it in supersymmetric theories and so on. So the point is that the more we have, I don't know which is done in extra dimensions, but in supersymmetric theories, it has a very rich phenomenology. Very rich phenomenology. You can connect with the low energy neutron data, high energy data, and you can do various things. You have soft leptogenesis, so and so, a lot of stuff essentially. Okay, and also there is a bound coming from the gravitational mass in supersymmetric theories. Okay, so there is a limit on the lightest right-handed neutrino coming from because of the gravitational decay. So it's around 10 power 9, which is very close to the lower bound. Okay, but those are all ancillary because you are having supersymmetric theories and so on. But independent of that, just as a mechanism, apart from the detailed calculations and everything, this seems to be easy. As a mechanism, it works very well. So this seems to be working in most cases, as far as we know. Okay. So this could be one of the requirements that we can insist that if you have a standard model, this should have some extension, either in terms of right-hand neutrons. Okay. So any questions? So we are almost done with all the things, right? Baryon, anti-baryon asymmetry, and Stokes we are done. We want to finish last week itself. So Thursday onwards, I'll start with one physics we understand, which is essentially supersymmetry. I'll start with supersymmetry, and I hope to finish in a few lectures. I don't want to, because it can be a full 1 semester or 2 semester course supersymmetry, but I'll do it in the best possible, easiest possible way. Okay? I'll try to do it in the easiest way. Like I'm doing everything. Okay, I'm not doing good. Okay. So Thursday onwards, I'll start with 16. Any questions on so far on all the problems? Do you have any other problems in standard model? Other than what we discussed? Any other problems or something? Huh?
You have a hierarchy.
Yes.
Hierarchy.
I didn't discuss it. It's pretty complicated actually. Yeah. Now that 5 is raised, maybe I'll just use 5 minutes to explain the Yukawa hierarchy. Just like the hierarchy problem, I mentioned it briefly. I'll also mention the Yukawa hierarchy. I'll talk about one particular solution for that. Okay. So let's just take Yukawa matrices and let's take top Yukawa matrix. And you need to generate. Let's do it only for leptons is a much more complicated problem. Let's do it for hadrons. Maybe leptons we'll do when we discuss neutron masses. Okay. So let's just take, I'll divide it with top Yukawa. Okay. So I have one here. And then I have lambda 4, lambda 5, lambda 5. I'll tell you what lambda is. Okay, I'm writing it right. Lambda 4 and 8. Lambda 9 smaller, 7, 5, 5. Symmetry. So suppose if I assume Yukawa matrices. Why this is interesting is because Yukawa couplings are being probed by LHC right now. Essentially, we are now having mu tau Yukawa probe, nu e Yukawa probe, and so on. If and lambda is nothing but the CK matrix. The CK matrix can be expanded in terms of lambda 1, lambda cube, lambda square 1. Some coefficients are there. But let's not worry about it. Let's take order of magnitude. So if lambda is the Wolfenstein angle, it's called the Cabibbo angle or the Wolfenstein angle. In Wolfenstein parameterization, is a very small number, 2.2 into 10 small. It's 0.22. So if you re-express your Yukawa mass matrices to generate this CK matrix, they take up the form which is highly suppressed here, Yukawa plus uptype form. Okay? And same thing you do for the down type of mass matrix. Okay, let's just leave it as 1. So this is lambda square, lambda 5. I don't remember these numbers, but it can be expanded in some powers of lambda. Okay. So what it tells you is that mt by mu by mc is lambda power 4, mc by mt is lambda power 4, md by ms is lambda square, ms by mb is also lambda square. Okay, so the uptype is like the square of the downtype mass matrix. That's the hierarchy. Okay, the hierarchy of the uptype is square of the downtype hierarchy. Okay, the hierarchy in the downtype is much higher. In the uptype is much higher compared to the downtype. Now, if you have such large hierarchies, so quark masses have small mixing and large hierarchies. Okay, quark mass matrices have large mixing So this means the echo couplings are running amok. They are running around 6 orders of magnitude here. So they're running from 6 order, 6, roughly 6 orders of magnitude. They're going around 6 orders of magnitude. Echo couplings. So, is there a dynamical way to explain this large separation and the hierarchy of these things? This is also called the Fermi-Mass problem. There are 3 well-known examples. Okay, why people try to do it. Okay, the first one is assume that they are all same mass matrix at the high scale. Okay, so this is a very influential paper by Prof and Nilsson, and also by Weinberg also whatever. Okay, so I will discuss these 3 solutions first. Only one of them works. As usual. Okay, yeah. The first solution. So people have thought about this. Okay, so in great detail. Assume that they are all same mass matrices, one mass matrix at the high scale, some scale around gut scale or something like Planck scale or whatever it is. So they have some form, maybe close to unity. All of them are same order 1 entries. It's a unit matrix essentially. And then your RG evolution, meaning your recover RG equation from the high scale to the weak scale will dynamically generate these hierarchies. Okay, will generate these hierarchies. Okay, this is one of the first ideas which was tried. Now, okay, red light, it doesn't work. Okay, it doesn't work. Second, random matrices. So assume that echo matrices are completely random. So you have a distribution essentially. Okay, you have a distribution. Okay. All order 1 entries, random matrices. And you ask the question whether they have a structure, what is the success ratio, if it is random or if it has some structure. Structure in the sense that it has some hierarchical structure, all of them are 1 or something, or all of them are equally random. Okay, all of them are equally random doesn't work very well compared to if you have some structure. So points out okay, completely random is not completely random. I mean, it's not success ratio. You can fit it, the data you can fit it, but you can say if it's a random distribution, you'll have some success ratio essentially. But if you have a structure, the success ratio is much higher. Okay, so it really points out to have some sort of structure. Third one, assume some symmetry. This is also called horizontal symmetry. So what is a horizontal symmetry? It's a flavor symmetry, but on now generations. Okay, so you assume some symmetry over generations. Like for example, U, C, P have some symmetry. Okay, B, S, V have some symmetry. Electron, mu, tau have some symmetry, some representations. Okay. Okay. These seems to be the way to go. Actually, this seems to be working pretty well. So one of the examples is propagation mechanism, which I can discuss at some point. Okay. So, but these are complicated models. Actually, they look simplified. They look. You assume some. The simplest of them is the propagation with a simple U1. You don't need to do. If you want to use a full flavor symmetry, which we have seen is to be SU3, you don't have to use the full SU3. A simple U1, extra U1 will work. It's called U1 propagation, which will work actually. These models are also equivalent to models in which you localize an extra dimension. Okay? You localize at different points in extra dimension. So these can be correspondent to, there is a one-to-one correspondence to these models and localization models in extra dimension. Here, in this case, you have some extra fermions. In this case, you have some extra space. Okay, as I mentioned. Okay, extra space actually. Okay. So maybe at some point I'll discuss this model. So the problem with standard model is you don't have explanation why this happens, why this large hierarchy between this order one parameters. And if you want to make it work, the basic idea seems to be that you need to have some sort of symmetry. The best way to go about is to have some symmetry. Now there are various versions of this, like propagation and localization extra dimensions, quote unquote. And another version of this is also called clock code. So on and so forth exists. So there are many of these versions. Yeah, you have any questions on this part? So people also use this propagation will introduce a lot of fermions and extra heavy fermions and extra flavons, some scalar fields called flavons. So people ask the question whether the flavons can be dark matter and so on. So those ideas are also being used. Because dark matter is free for all. So anything can be put into there. So yeah, so essentially you can any model you can try to ask the question about dark matter. Because we don't know what it is. Any further questions? Yeah. Okay. So next week I'll start with subsymmetry.